Hi, my name is Gabrielle Taylor. I'm going to be doing homework for Part A. So we have 3 tanks in series. So we have a Qn coming into this tank series, and then we have a Q1 leaving this first tank, and then a Q2 leaving the second tank, and then a Q3 leaving the third tank. All the tanks have the same cross-sectional area, and they have the same size of the drainage hole. The cross-sectional area of that will be the same as well. So what we want to do is we want to do a linearization of this. So we can look at the differential equation. So we have so the area times dH dt, which is going to give us a volume, and then that is equal to Qn minus 2gh, it's the square root of 2g, and then we have out times height squared. So this is not a linearization. This is not a linear equation, because a linear equation would mean that it would be a first order equation, and our height is in 1/2. So we need to make it a first order so that we linearize it. So let's do that. So we're going to have dH dt on one side. So it's going to be 1/a Qn, and then we're going to make this an alpha because it is a constant variable. So then alpha over a, and then h to the 1/2. And so the next thing that we want to do is, when we want to linearize this, we want to have a steady state, and we want to have the initial. So we need to do the initial minus the steady state pretty much. So we have is our QH is going to be equal to 1/alpha Qn minus alpha h bar 1/2. And so h bar means that it is at the steady state. And then we're going to have this plus, we want to add the derivative of this. So the derivative is 2/h bar to the 1/2. So if you don't know, so h prime is equal to h minus h bar. So h is the height at that current time, t. H bar is going to be your steady state, and then h prime is the subtraction of that. So this will be h prime here. So next, what we know is that if dH dt prime is equal to 0, then that means that h minus h bar is equal to 0 as well, because there is no change. If there's no change in height, that means there's going to be no change, so they'll be the same. If they're the same, then this here will equal 0. So let's do that. So we have 0. We have 0 equals 1/a Qn minus a, and this is that, and then we have just h bar. Yep. We have h bar to the 1/2. Right, so our Qn is at steady state, and then we have h bar to the 1/2 is at this 0, right? So now we want to subtract these two together so that we can get pretty much our dH. So our dH dt, this would be our prime, and then 1/a. We're doing Q minus our Q bar, so that's going to be a Q prime in, minus alpha over A, and then it is going to be our H prime over our 2 H bar to the 1/2, right? So now we are in a first order since our H prime is that. So now we can do is the Laplace transform of this. So once we take the Laplace transform of that, we're going to get an SH is equal to 1 over AQ in minus alpha A to, I can rewrite this better, over 2A H over 2H times H here. So now we are going to solve for H. So we have H is equal to S plus alpha over 2A H bar. And then is equal to 1 over AQN. So now we're going to just solve for H. So I'm going to copy this here. Copy. And then we can go to the next page. Okay, so now we have is our H is equal to Qn, and then we're dividing, so we have is S, we have SA plus, we have Q, our A's cancel out of this function, so then it's 2 H bar. Okay. Now, after this, what we want to do is we want to divide by the alpha divided by 2 H bar by every factor in our equation, in this fraction, pretty much. So then we have is going to be is 2 is equal to 2 H bar over alpha. This is going to be times Q. And then we have is 2A H bar over alpha times S plus 1. Okay, so we have our function here. And this function is now a Laplace transform. So it looks very similar to a Laplace transform of a first order function, which is k over tau, which k is going to be your gain, and then tau is going to be a function of time, s plus 1. So from this, we can see that k is going to be equal to 2 over h bar over alpha, and then tau is going to be 2a divided by to the square root of h bar over alpha. So these are our k and our tau. Now we can have this is we can so these are what we're going to use to solve, and this is going from a height to a flow. So this is just one part of this equation, because you are having your change in your height due to time, but we also have a flow rate. So now we need to do the flow rate of this equation. So we have is, so if we look back at this, we can see that our Q1 is changing due to its due to the height. So it is going to be, we'll just do 1 for now because they're all related to each other. So Q1 is equal to alpha of h squared. And then we're going to do very similarly what we did on the other one as well. So it's going to be Q1 is equal to alpha and h2 bar plus h prime over 2 bar, right? And then we're going to have here is our next one our Q bar there, and then our Q prime is equal to alpha H prime over 2 H to the 1/2. And then we have as our Q for our Laplace transform, we have it as Q over 2H bar 2H. And now we see that this is K, right? So this means that this is 1 over K. So now we have this, which is a, let's just write this as 1 over K. So this is a flow to a height, right? Flow to a height. So now let's think about ourself, right? So we want to go from, so let's say we want to know what Q3 is, right? We want to know from Q3 is, so let's say we want to know what Q3 is. Based on, we need to know that information of what H3 is, right? And then to get that information, we need to use, we're going from a height to a flow, right? So from that, we know that that is going to be our K over tau S plus 1. Now I'm going to move this over because we're going to do it for, again, so how do we get H3 based off of this info? Well, from H3 we're going to get our Q2. And so now we're going from a flow to a height, right? So we're going from a flow to a height, we're going to need 1 over K. And then let's say we want to do is to find Q2, we're going to be doing H2, and then we're going to be going from a height to a flow, so we're going to be doing K tau S plus 1, and then to get that, we are going to have as our Q1. Our Q1 is going to be 1 theta, right? And then let's move this over even more until we finish it. So then, after we have our Q1, to get our Q1, we have to do is our H1, and then that is a tau over S. These are not Q. Okay, so these are a little messed up. So this one here is going to be is height 3. Height 3 is based off of the Q2. And that one is based off of the height 2. And that one is based off of the Q1. And the Q1 is based off the height 1. And the height 1 is based off of the Qn. Okay, now, this is the order it's supposed to go in. So let's think about it. We're going backwards. So we have the height, and we want to go to the flow. So height to flow is going to be this here. And then Q, then a flow to a height is this one. And then a height to a flow is this one. And so on and so forth, right? So lastly, we have is our Qn, right? So we're doing height 1 to Qn, and we have this, right? So Now if we look at all of this, and we have our function all together, right? So we're going from Qn to H3. We just need to do is Qn is equal to H is K tau S plus 1 times tau S plus 1 tau S plus 1, right? So after that, we're going to cancel out our K's. So these cancel out, and then we just have this. So then we have is K is equal to tau S plus 1 to the third power. And then this needs to be height 3 is equal to Qn times that. So then our Qn here times our H3. Okay, so now let's look at this. So our original transfer function was a first order. Now it's to the third power here, which let me write this a little better. Now it's to the third power here. So that means we're in a third order transfer function. Now it makes sense because we have 3 tanks in series that we're going to need this third additional. Like it's a third order based off of being multiplied 3 times. So now we have going from the height 3 to Qn. So now there's a relationship between our Qn to our height 3. And then this is it. Hello. So we are going to be deriving the feedback controller to this function, right? So I did a block diagram, so I will just go over this. So we first have our height set point right here. Right here. And that is going in, and we're going to get an error. And that error is going to help affect our proportional controller of KC. That is going to control our Qn. And then we have GP. That is going to be our process, our whole process. So it's going to be condensed into one term. But that is a process control. So then it's going to put out a H3. So when our height 3 of the tank comes out, it's also going back up to the comparator. The comparator is going to compare the height set point to the height of tank 3, and that will give an error. Since that causes an error, that will go and change the proportional controller either more or less based off of if that height set point is close or not close enough to the height set point. And that will go in and change the flow rate, which is our Qn, to our process. So what's going to happen is we want to do another short form of this. That is called a feedback control, right? So our process is a feedback. So we are doing a feedback controller, which is our GFB, right? And that is going to be our height of 3 and our height set point. So our height set point is going in, and then all of this in the center is going to be our feedback. And that will be our height of 3. So what we can do is we know that for our height of 3, what parameters multiplied by this is GP times KC times our error. We know that our error is going to be our height set point minus our height of the tank at 3. So GP times KC, and then we have our height set point minus our height of tank 3. Now, if we want to solve for H3 on one side, what we can do is H3 is going to be 1 plus GPKC, and then we just have GPKC of the height set point. So we also know that we have our feedback controller, our process feedback controller, right? So we have is H3 times our feedback controller is equal to our height set point. Now, we know that to solve for GFB, we get the height of set point over H3. So now, let's do it to the terms that we have already created. So, it is going to be H3 over HSP, and that is going to be GP HC over 1 plus GP KC. So we know GP because we did the Laplace transform to find that we had a third order transfer function. So now we can plug that in that we did previously in this video. So we had, it was K, well, I just get back. So K over tau S plus 1 to the third times Kc over 1 plus K tau S plus 1 to the third Kc. Now, if we multiply our entire fraction by tau S plus 1 to the third, then we can get it out of the denominator and some of the other fractions in there, right, to make it look cleaner. So we have is at the top, we have KCK, which this is H3 over the height set point. We have KCK over tau S plus 1 to the third plus KCK as well. Now we can just multiply over so we can get our height set point, right? So our height to the third is multiplied by our height set point. So this is going to be our transfer function of that feedback controller, right? So we now know our height of 3. Now what happens if there is a unit change to this? So if there is a unit change to this, like a step unit change, then our height set point is going to be equal to 1 over s. Now, since it is 1 over s, we can make another function to this. So we have our deviated function of our height set point, of our height 3, and we are going to change our height set point. So we have Kc over K over tau S plus 1, 3 plus KCK, and then we multiply it by 1 over S, which is our step change, our unit step change, right? So from this, what we can do is our final value theorem. So our final value theorem says we have a step change times our function, and if we take this to the limit of s approaches 0, this will equal the limit as it will equal your function's value at infinity. So what we can do with this is that we know if we take the limit as s approaches 0 as s our function, it will equal the limit as t approaches infinity of our function of the deviated height at 3. So what we have to do is now we plug in our function into this here. That will give us the value of our function that will give us the value of our function that we want. that will give us our value of 1 at infinity. So what we have to do is we do the limit as s approaches 0. We do is kc times k over tau s plus 1 to the third plus kc k. So what happens is we have is s is approaching 0. So if s approaches 0, then tau s will be 0. So then we can rewrite this as kck over 1 plus kck. So this is going to be our function. So from this, what we know is that if our controller, so pretty much what we have here is our proportional controller gain. And we have our process gain here. So if we have a proportional controller gain and that proportional controller gain increases, what will happen is that our denominator, the 1 plus, will become negligible because it will be so big that it will be approaching 1. So when that approaches 1, that will be 1, the same value over the same value, which will equal 1. And this is good for us because what we want is a step change value of 1 is going to also have a deviation factor of 1, a deviation value of 1. So these are good to have these two together. They're proportional, right? But if we look at this and we have a smaller kc or proportional gain, what's going to happen is that value of 1 at the bottom will be dominant, right? So if we have a smaller value of that, the bottom is going to be very dominant, and that is going to cause it not to equal 1. Our deviation will not equal 1, and since that, we'll have a 1 step change in our deviation factor. Our deviation value will not be 1, so that will not be proportional. So that is a problem that we might see occur. So that is the end of homework A. Thank you.